Okay. Is this working or not? Okay. Where's my stick? So, my name is Joshua Kaplan. I'm first year PhD student, and I'm presenting my work on segregation effects in granular collapses that I've been doing here at Cambridge. Come on. Oh dear. Technology never works when you want it to. I don't understand things. What is going on? Sorry, this normally works. Come on, I've got two copies of that. Stupid. Yeah. Right. Is that working? Yeah, there we go. That's better. So, thinking about granular collapse, thinking about a mass of granular material falling vertically, spreading outwards, like this rock slide we've got here in Devon. Thing about them is this is relatively small. They can get quite big. Like this guy is in the Black Hawk landslide in California. It's about 5 miles long, 2 miles wide. And if we look purely at the energetics, something like this shouldn't actually exist. So we try and understand this via lab scale experiments, such as this guy here, which is one of mine, where we have consider just a simple cylinder of granular material and let it fall down and make a nice little mess there. So what the segregation effect is taking the fact that real materials are actually polydispersed, got lots of different types of particles there. This leads to segregation effects, which have some effect on the flow, which you don't fully understand. For simplicity, we're only looking at size segregation. You also got other effects based on different densities and shapes, but they make things more complicated. So, quick revision for people who are not familiar with segregation. Two effects are important in this sort of problem. First of all, is kinetic sieving. So, as our flow spreads out, you get holes appearing in the granular structure. Small particles find it easy to just fall in. Big ones get a bit stuck. And we have the second effect called squeeze expulsion, where particles just get random forces and can get pushed upwards. So the net result is small stuff sinks to the bottom, large stuff rises to the top. So thinking about these simple collapses with one type of material, two main papers done in 2004, where they looked at the effect of varying the aspect ratio, so the initial height over the initial radius, and saw what happened, and thankfully they broadly agree with each other. So key results, they found nice power laws with the, scaled the non-dimensional run-out distance against the aspect ratio. So for tall ones, we get this square root law. Small ones, it's linear in the aspect ratio. So yeah, the exact coefficients depend on your experiment. Other effects, if we look at initially horizontal layers, they don't mix. So this column was initially just striped dark and light, and it stayed that way throughout the collapse. So we'll see what happens when we start bringing segregation into that. Other things, surface roughness doesn't really play too much of an effect. The choice of material is unimportant. We get as the collapse spreads out, it goes out at a nice constant rate before decelerating very rapidly. And if we look at the side of the material, we find there's a central region which doesn't actually move during the collapse. So, other work, yeah, modeling, other geometries, lots of stuff. So, this is technically an old version of my experimental setup. Have a column of material. We look at two different layers of material, because if we try to attempt to mix these things, they'll just segregate out as soon as you try and pull them into the column. Up here is a laser scanner that gives us some height profiles with time, and there's a high-speed camera which you can't see in this photo. So parameters, I'm using Ballatini here because it's nice and round, smooth. I'm using a rough surface to try and prevent the badging just rolling off to infinity. Range of masses, I'm keeping the mass ratio of the two different layers the same throughout for simplicity again. So let's look at some videos. So this is an inversely stratified column with large material at the top. So this is stable to segregation effects, large already at the top, and spreads out. We don't see any sort of mixing between the layers here, which is what you'd expect from both the monodisperse case and segregation. Spreads out quite nicely like that. Not much more to say there. If we look instead, the layers the other way around, so the small stuff is on the top, so we expect segregation to end up with it. Small stuff sinking to the bottom, large stuff rising. And as you can see, as we spread outwards, we will start to see some segregation effects here. But this is actually, the collapse is so short that it doesn't get, it's not complete. Also, there's possibility there might be some sort of radial structures where the segregation occurs, but it might just be an illusion. Haven't investigated that fully yet. So if we look inside these inverse ones, no mixing as we expected, and normal ones, we're starting to see some segregation with large particles rising upwards, again as expected. If we track the front position with time, we see again we get with these inverse ones we're getting this, which you call it constant expansion rate, as with monodisperse, reasonably quick deceleration out there. Notice that this spreading rate is independent of the column height, which is not intuitively obvious, but it is what was found with monodisperse columns. If we look at the normal ones, where you'd expect to see segregation effects, we're getting exactly the same looking behavior. Again, this constant spreading rate heading up to there. So if we plot everything on the same graph, along with some monodisperse ones for comparison, it's all pretty much the same behavior. There doesn't appear to be any particular differences in how these flows spread outwards. We can do a bit better than that. So these are just the very tallest columns. I rescaled the time by the free-fall time scale, which is square root of initial height over g. On the top axis is the non-dimensional run-out distance. I've scaled this by the square root of the aspect ratio, and everything quite carefully collapses onto one nice curve here, which is good. From this, we also see that we're expecting this run-out, the spreading speed to scale like the square root of the initial radius times g, but we've only looked at one initial radius, so I can't actually confirm that for these columns. Look at the run-out distances. We can try and plot these power laws. Really need a bit more data before we can say of any confidence, particularly down at this lower region where I've got almost nothing. That's a limitation of the cylinder radius that I've been using more than anything. So with the high-speed footage, I can use PIV to get the surface velocities. So this is a time series along a radial slice, radial distance along here, time going upwards. This line here is our constant spreading speed. Looks nice and constant here. We can also see up here that the flow stops from the center outwards along this little stopping shock. These flows are actually going pretty fast. You can see in the central region here, we're getting up to speeds around 1 meter a second, which, considering these columns only about 25 centimeters tall, is pretty fast. If we look at them, this is an inverse column. If we look at a normal column, it's pretty much the same. Speed's the same, everything looks the same. Monodisperse. So yeah, there's not much difference in the dynamics of these collapses, regardless of what we try to do with them, or at least at these tool aspect ratios. If we look at the height profiles with time, here's a relatively early screenshot, all identical. In the middle, there is some sort of slight difference here. Not entirely sure what's going on here. It might just be the way the laser scanner is picking up the different types of material. And at late times, yeah, it all comes out as the same. Limitations of what I've been doing, only got a limited range of aspect ratios. So for smaller ones, it might be different. For even taller ones, different. Only one value of the initial radius, so can't confirm that the scaling of the spreading velocity is what I think it is. Only one mass ratio between the two layers. If that were different, you might get different behavior. We haven't looked at any of the other possible segregation types from density or the shape. So density segregation, you expect dense material to sink and less dense stuff to rise based on the energetics. So you expect the same sort of differences that we saw earlier. With shape effects, you might expect to get some sort of fingering instability as the front spreads outwards. But you need to investigate that a bit more. And the key one here is this limited value of the initial height, because the timescale, that is what sets the timescale of the collapse. And from what we've seen is that the collapse is coming so fast that we're not getting complete segregation, and that might be affecting why we're not seeing much differences between the two things. So conclusions, everything looks pretty much the same. Same sort of runouts, same sort of velocities, possible some variation in the profiles during the collapse, but not entirely clear. The key thing is the columns I've been looking at are so far too fast for complete segregation to occur. So if you do choose a column height where that is possible, like in real geophysical situations, there might be some differences. So yeah.
You mentioned that the bed is rough.
Yep.
What particle diameter roughness is the bed compared to the actual particle?
It's similar to the larger particle scale. So it shouldn't have, based on the wander dispersed stuff, it shouldn't have too much of an effect, because the particles quickly fill up the gaps and the bumps on the surface, and you end up with something that looks a bit like an erodible base. We'll have to use a rough surface, because if you try anything smooth with round particles, they just roll off the table and make a mess everywhere.
So, with your particle segregation, have you done exactly 50-50 split each time?
Yes, by mass.
So, maybe what you should start to look at is, instead of going from top to bottom, you should go from side to side, because as you said, you've got this internal conical shape which doesn't move.
Mm-hmm.
So the majority of what's in the bottom of that 50-50 split, especially as you get into a large one, isn't going to move anyway, or it shouldn't. You think?
Quite a lot of it does actually move if you look at some pictures. So that column would have been about 12 centimeters tall, and is now 1 centimeter. Well, the white layer is 1 centimeter tall. It is a small region that doesn't seem to go very far, but it is quite small. I've thought about trying horizontal splits just for fun, but I never got around to doing it.
I'm just wondering if, with the various normalizations that have been done on the original experiments, was particle size part of the sort of way that people had actually non-dimensionalized the behavior?
So let's go back a bit. So this graph is various different particle sizes and shapes, in fact, and it doesn't really make a difference at all.
Exactly. So why would you expect particle size to actually make any difference in these experiments if they're not? If you see what I mean, if it doesn't make any difference in a sort of homogeneous system.
You might not expect the particle size to matter, but the fact that you've got two different types and there's segregation, so you're actually getting a mixing effect, which you don't see when you've only got one type of material. You might expect that to have some effect on the flow, whether possibly making it go further or inhibiting it, but it doesn't actually appear to be making much of a difference, which is kind of interesting.
What would be the characteristic segregation velocity compared to the primary flow?
That's one thing I haven't actually measured anything else, how fast these things would segregate normally. But yeah.
I think that the size of the grain can matter with respect to the length of the avalanche. If you reduce the size of the grain, maybe the segregation can rise up.
So if you've got a bigger size ratio between the two things, then you would expect segregation to happen faster, because particles can fall through much quicker. So yeah, you get issues. Smaller particles are much more of a pain to work with. the main reason why I'm using these particular sizes. And bigger ones just start rolling much farther. So there are experimental restrictions on the particles you choose. But yeah, these things do segregate pretty quickly, and just say pouring them into the sieve after the experiment. So,
Take one last question from Michelle.
After a while, everything seems to be tasting like chicken, irrespective of the size of the chicken. I just wondered whether, seriously, I just wondered whether breakage in the actual geophysical phenomenon might play a role, because I imagine these large boulders falling to the mountain, and eventually they end up being ground up.
so yeah, you would expect that because these sort of things do fail by a slab falling off and breaking up. Unfortunately, that's much harder to do in the lab, particularly if you want to repeat your experiment. So yeah, it would probably have an effect, but I haven't been able to look at that with my model.
I think we should close the session. I'd like to thank this speaker and all other speakers for